Hello everyone, and welcome to a new video about exciting math theory brought to you by the MZH team. Today we're gonna see how we can solve second degree equations with one unknown. This problem is also known as the quadratic problem, for which the so-called solution, the quadratic formula. This is also known as finding the roots of a polynomial of degree 2, which will lead eventually to the factoring of polynomials of degree 2. So without delay, let's get into this. And before going into solving the equation at hand, we're gonna need some prerequisites for this video. And this is what I highlighted in red here. So we're gonna need three formulas. The first two are known as the remarkable identities of order 2. And I'm pretty sure most of you will be familiar with these first two formulas. So the first one is a plus b squared is equal to a squared plus 2ab plus b squared. And the second formula is a squared minus b squared is a minus b times a plus b. The third formula is actually an application of the first one. Basically it says for any x and for any alpha, x squared plus alpha x is equal to x plus alpha over 2 squared minus alpha squared over 4. And a way to prove that, try to start from the hand right side and try to apply 1 to arrive at the left hand side. So I'll leave that as an exercise for you. It's pretty straightforward. But now let's get to the main problem that we want to solve. So as you can see here, we want to solve the equation of the general form ax squared plus bx plus c equal to 0. And we will name this equation E, and we will also call ax squared plus bx plus c as p of x. And this will make our lives easier in the derivations that will follow. Let's also call S the set of solutions for this equation. Our approach here will be to start by eliminating the obvious case, which is a equal to 0. So in that case, you would see that the quadratic term x squared would disappear, and in that case we will have p of x is equal to bx plus c, which means that p is now is a polynomial of degree 1. And we already derived how to solve an equation of this form. And if you are not familiar with that, please refer to theory lesson number 1 video that we did specifically on this topic. Now let's get into the interesting case, which is a different of 0, in which case p is actually a polynomial of degree 2. And we start by factoring by a in the expression of p of x, and that is allowed because a is different of 0, because we're gonna divide by a in the b term and the c term, and that is only possible if a is different of 0. So we're already using that assumption here. As you can see, it's pretty simple. First line is p of x is equal to a times x squared plus b over ax plus c over a. So nothing really difficult in this step. Second line, we're gonna try to use the prerequisite number 3 that we saw at the top, where we said that for any x and alpha, x squared plus alpha x is equal to x plus alpha over 2 squared minus alpha squared over 4. And as you can see in this example, our alpha is actually b over a. So we're gonna apply the formula for this term, x squared plus b over ax, and b over a would be our alpha. So in that case, this term will be equal exactly to this one. And it'll be equal to x plus alpha over 2 squared, and alpha is b over a, so it'll be x plus b over 2a squared, minus alpha squared over 4, but alpha is b over a, so it'll be minus b squared over 4a squared. And we didn't touch the c over a, so we put it there. And from here, we just go and try to put these two terms into the same denominator in the third step, and therefore we get the formula here. So p of x will be a factor to x plus b over 2a squared minus b squared minus 4ac over 4a squared. And for those of you who are familiar with this topic, you will start to see some familiar terms in the expression of p of x, namely b squared minus 4ac, which we will call from now on delta. So delta is b squared minus 4ac, and this is a very, very important parameter, and you'll see why shortly. Therefore, now if we go and substitute delta in the expression of p of x, we get this very important formula for a different of 0, which is p of x is equal to a factor to x plus b over 2a squared minus delta over 4a squared. So we can't go from this point on without making further assumptions. So this is the further you can go in the expression of p of x when a is different of 0. So now what we're gonna do is we're gonna see how we can move forward by analyzing the sign of delta. So the sign of delta will determine the type of solutions we're gonna get from this equation. The first case, which is the simplest, is when delta is negative. So when you calculate b squared minus 4ac, let's assume that delta is negative. So in that case, and as you can see here, the equation E will be equivalent to this term, x plus b over 2a squared will be equal to delta over 4a squared. And let's analyze the left-hand side first. So x plus b over 2a squared, as you all know, is a positive number because any number squared is a positive number. But this positive number now is equal to delta over 4a squared, which is a negative number because we assume that delta is negative, and we know that 4a squared is positive, so delta over 4a squared is negative. And from there, we can deduct that this is a contradiction because no non-negative number can be equal to a negative number. And therefore, there is no x that can verify such an equation. And therefore, we can say that the set of solutions S is actually the empty set. And also, we can also notice that the polynomial p cannot be factored for delta negative. All right, so let's see the other case where delta is positive. So if delta is positive, what is changing here is that now, if you focus on this formula now, you would see that p of x is equal to a times something squared minus something squared. And this something squared is actually square root of delta over 2a. And we're gonna have to use the prerequisite number 2 in order to develop this expression further. And if you recall, prerequisite number 2 is that the difference of 2 squared is actually the product of the difference and the sum. So we just apply that here, but our a and b are now the a is x plus b over 2a, and b is square root of delta over 2a. And that's what we're writing here. So p of x becomes a times x plus b over 2a minus square root of delta over 2a times x plus b over 2a plus square root of delta over 2a. And that we derived from prerequisite number 2 for your reference. Then it becomes easy. We just put these terms here under the same denominator. And we get the expression here. And from there, we're gonna name the term minus b plus square root of delta over 2a as x1, and we're gonna name minus b minus square root of delta over 2a as x2. And these are the expression of x1, x2, highlighted in red. And if we substitute the values of x1 and x2 in the expression of p of x, you can see that p of x can be written as a times x minus x1 times x minus x2. And this is very important. So we were able to write p of x as a factor of two polynomials of degree 1, and this is what we call a factoring of p. And now in order to solve the equation, we just have to go and say that p of x is equal to 0 is actually equivalent to say that x minus x1 times x minus x2 is 0. And we know that if the product of two numbers is equal to 0, then one of the two numbers has to be 0. So in this case, either x minus x1 is equal to 0 or x minus x2 is equal to 0. In which case x is equal to x1 or x is equal to x2. In which case the set of solutions has two elements, x1 and x2, for which the expressions have already been given here. Alright, so we were able to solve the equation in the case of delta positive. Let's see now the case when delta is equal to 0. And for that, we're gonna have to go up to the main expression of p of x here. And you'll see that if delta is equal to 0, this term actually goes to 0. And therefore, what is left is just a times x plus b over 2a squared. And that's what I wrote here. So in the case delta equal to 0, p of x is a times x plus b over 2a squared. And now let's call x naught minus b over 2a. And then if we substitute that in the expression of p of x, we find that p of x is actually a times x minus x naught squared. And this is the factoring of p for delta equal to 0. Now, if we want to solve the solution p of x equal to 0, that will be equivalent to x minus x naught squared is equal to 0, in which case either x minus x naught is equal to 0 or x minus x naught is equal to 0, which is equivalent to say that x is equal to x naught. And from there, the set of solutions has one element, x naught. In this case, x naught is called a double root of p, or a root of p with multiplicity 2. And that is the case because, as you can see from this expression, x naught appears in p of x as a term squared. If we had p of x just equal to a times x minus x naught, then x naught would be just a simple root of p. But in this case, x naught is a double root of p. So in terms of solving the equation, it doesn't really matter because you found the solution, but this concept is very important in polynomial theory that we're gonna see later in our next videos. So we have developed the main or the core theory of how to solve an equation of second degree. Now let's see some useful remarks. So the first remark that I want to discuss is a very useful trick where just by looking at the coefficients at hand, you can actually determine whether the equation has solutions or no. So let's start the discussion. So we know that delta is equal to b squared minus 4ac. And let's assume that AC is non-positive. So in that case, minus 4AC is non-negative, and from there we can see that delta will be non-negative because b squared is actually non-negative. So by just assuming that AC is non-positive, we came to the conclusion that delta will be non-negative. Let's decipher what AC non-positive means. AC non-positive means that A and C have different signs. So if A is positive and C is negative, or the opposite, you will have AC non-positive. And let's see what delta non-negative means. It means that E has at least one solution, because we saw that in the case delta positive and delta equal to 0, we have either two solutions or one solution for the equation. Now let's see another case where if you notice that your coefficient B is even, then you can simplify some of the calculations of delta and the roots if they exist, and we'll see how. So in case B is even, we can write that B is equal to 2B prime. And in that case, if we start with delta is equal to B squared minus 4AC, we can substitute B by 2B primed. And in that case, we will get that delta is equal to 4B prime squared minus 4AC. And we can factor by 4 and say that delta will be equal to 4 times b prime squared minus ac. And we're gonna call this term delta prime, which will lead that immediately delta will be equal to 4 delta prime. And delta prime is given by this, is b prime squared minus ac. And because we have delta equal to 4 delta prime, you'll notice that operating on delta is the same as operating on delta prime, and that's what I try to express here by this equivalency, that if delta is positive, it is equivalent to delta prime is positive. So calculating delta prime is same as calculating delta. Now let's see the cases that we developed before. We saw that for delta prime positive, the root x1 is given by minus b plus square root of delta over 2a. And let's replace b by 2b prime and delta by delta prime. In that case, we will have x1 is equal to minus 2b prime plus 2 square root of delta prime over 2a, which will be equal to minus b prime plus square root of delta prime over a. And from there, we can also derive the expression of x2 by the same substitution. And we get these expression for the roots of b, which are given by x1 is equal to minus b prime plus square root of delta prime over a, and x2 is minus b prime minus square root of delta prime over a. So why is this useful? So you can see that if we go and calculate delta prime, already we're using b prime instead of b, and b prime is half of b, so this will be easier to calculate. And you can see also that the fourth term is missing. So it is easier to calculate AC rather than calculate 4AC. You can also see here in the expressions of x1 and x2 that we're using b prime, which is less than b, and we're using delta prime, which is less than delta, because with delta is 4 delta prime. And we're dividing by a rather than 2a. So all the calculations become simpler when b is even. So that's why this is an important trick to have It'll simplify your calculations and make your life easier. So let's go to the other case where delta prime is equal to 0. We saw that in that case the double solution for the equation is given by x naught is equal to minus b over 2a. If we substitute b by 2b prime, we get x naught is equal to minus b prime over a. And again, the simplification here is that we don't divide by 2, and we're also using b prime instead of b. And if delta prime is actually negative, there are no solutions to the equation. All right, so let's summarize what we've seen up to this point. So the idea of this video is we want to solve p of x is equal to ax squared plus bx plus c equal to 0. So we saw that if a is equal to 0, then we get a first degree polynomial, which is bx plus c. And we saw in our previous video how we can solve such an equation. But just for your reference, I'm including the solutions here in this case. So if b is different of 0, we get s, the set of solution is minus c over b. And if b is equal to 0 and c is different of 0, we get the empty set as our set of solutions. And if b is equal to 0 and c is equal to 0, then our set of solutions is actually all the real numbers. Now, for the other interesting case, which is a different of 0, we get actually a polynomial of degree 2. And the first thing we do, so this should become a reflex, whenever you see a second degree polynomial, you should start by calculating delta, which is b squared minus 4ac. And based on the sign of delta, you can derive the solutions of the equations. We start with the case delta negative, in which case the set of solutions is the empty set. If delta is equal to 0, then you get one double solution, which is given by minus b over 2a. If we name this solution x naught, then a factoring of p would be a times x minus x naught squared. And the last case is when delta is positive, then you will get two solutions to the equation given by x1 equal to minus b plus square root of delta over 2a, and x2 is equal to minus b minus square root of delta over 2a. And the factoring of p is given by a times x minus x1 times x minus x2. So this is a very important chart to have. It will make your life easier when trying to solve an equation of this form. Let's see now if you understood this lesson, and let's apply it to some real examples. So let's start with this polynomial, which is given by 2x squared plus x plus 1. And let's also try to derive, just by looking at this equation, whether it has solutions or not. We saw in remark number 1 that if AC is non-positive, it means that this equation has at least one solution. So in this case, A is equal to 2. So A is equal to 2. B is equal to 1. And C is equal to minus 1. So A times C is minus 2. Or we can say that A and C have different signs. These two statements are equivalent. So we know, without even calculating delta, that P of x is equal to 0 has at least one solution. And if you want to be sure of that, now we can go and calculate delta to know exactly what this solution is. So we know that delta is b squared minus 4ac, and we can see that b is not even, so we cannot use the shortcut delta prime, so we're gonna have to use delta. So delta is b squared minus 4ac, and that's what you see here. So 1 squared minus 4 times 2 times minus 1. And delta, if you calculate that, it'll give you 9, and 9 is positive. Therefore, we know from this chart that if you have delta positive, you're looking at this. In which case, we know that the equation will have two solutions, and we just have to calculate that. So in this case, we're lucky because the square root of delta is easy to calculate. It's just 3. The solutions are given by x1 is equal to minus b plus square root of delta over 2a, which is minus 1 plus 3 over 4, which is equal to 1/2. X2 is equal to minus b minus square root of delta over 2a, which is minus 1 minus 3 over 4, which is minus 1. So we solve this equation, and you can actually go and substitute the values of x1 and x2 in the expression of p of x and see if p of 1 over 2 and p of minus 1 are actually 0. We can actually do it here quickly. So p of 1 over 2 is actually equal to 2 times 1 over 4 plus 1/2 minus 1. 2 times 1 over 4 is 1/2 plus 1/2 is 1 minus 1 is equal to 0. So this works. You can also try and calculate p of minus 1. So that will be 2 times 1, so it'll be 2 minus 1 minus 1, and this is equal to 0. So this is just a way to see if you didn't do any mistake in calculating the roots. If you missed a minus sign somewhere, or you didn't divide by 2a, you divided just by a or something. This is a very good way to see if you didn't mess up in some of the steps. All right, and from that point we can go and now try to derive a factoring of p, and we can use this expression here, a times x minus x1 times x minus x2, so which will yield p of x is equal to 2 times x minus 1/2 times x plus 1, which gives 2x minus 1 times x plus 1. All right, so let's go to example number 2, which is p of x is equal to x squared minus 6x plus 9. You'll notice here that b is actually even. b is actually minus 6, and minus 6 is even. So we can try and use delta prime instead of delta to simplify the calculations. But if we calculate AC, A is 1 and C is 9, we see that A and C have the same sign. So we can't conclude anything from that. Just be careful that if AC is positive, you can't say that if the equation have a solution or not. So we can't know just by looking at the coefficients. So we have to calculate delta or delta prime in this case to know if the equation has a solution or not. So if we go and calculate delta prime, if you remember, delta prime is b prime squared minus AC. And b prime in this case is equal to minus 3. So it'll be minus 3 squared minus 1 times 9, which is 9 minus 9, which is 0. And we saw that if you have delta prime is equal to 0, in this case, you have one double solution given by minus b prime over a. And that's what we will use here. X naught is given by minus b prime over a, with b prime is minus 3, which gives 3 over 1, which is 3. And as we did in the first example, you would want to see if you didn't mess up in the calculations and see if p of 3 gives 0 or not. So let's calculate that. P of 3 is actually 3 squared minus 6 times 3 plus 9, which is equal to 9 minus 18 plus 9, which is 0. So 3 is actually a root of P. And the factoring of P, we saw that P of x in this case will be equal to A times x minus x naught squared. So P of x in this case will be equal to 1 times x minus 3 squared, which is x minus 3 squared. Also, you can do another test to see if you didn't mess up in the factoring of P. You can write this and try to expand this by using prerequisite formula number 1, which is the first remarkable identity of degree 2, and write this as x squared minus 2 times 3x plus 3 squared, and this will be equal to x squared minus 6x plus 9, which is exactly the expression of P of x. Last example is P of x is equal to x squared plus x plus 1. In this case, B is not even and A and C have same sign, so we have to go the long route of delta. And in this case, delta will be equal to 1 squared minus 4 times 1 times 1, which is equal to minus 3. And delta in this case is negative. And we saw that if delta is negative, you're in this case, which means that there are no solutions of the equation and P cannot be factored. Thank you very much for watching this MZH video. If this math episode was helpful to you, please don't forget to like the video, share it with your friends, and subscribe to our channel. The notes are available for download. Just check the description box for the link. We would also like to hear from you in the comment section. We make sure to respond to every comment. See you in the next video to continue your zero to hero journey.